Hello everyone, welcome back to our channel. Yesterday we have discussed about the RAM implementation. So this is our Verilog project series and today we are going to design a 4-bit synchronous binary counter which will count from 0 to 15 since it is a 4-bit binary counter. So total combinations was 0000 up to 1111 that will count up to 15. So today we are going to design this in Verilog and along with that we are also going to create its test bench to verify this circuit. So before starting the implementation, we will see some details about the project and then we will going to start our code implementation part. So here they are describing that we have to design a 4-bit synchronous binary counter in Verilog. So these are all our features, like we have to include clock and we have to include active high synchronous reset. We have to include enable signal and also we have to include output, which is count output. And this is our behavior. Whenever your reset goes high, so your counter will goes to low or 0. And whenever your enable signal is 1, so your counter increment and otherwise it will remains as it is. So this is all the basic understanding of theoretical part, and let's start implementing the code in Verilog. So let me take you to the EDVA playground. So yeah, I have mentioned the question here also. So let's start the implementation part. So first of all, let's declare a module. So module, and let's say counter, and declare all the signals. So clock, reset, enable and count. Okay. Now declare all the ports. So input port was clock, input, wire, clock, reset, enable, yeah, and then our count was an output port. So output, reg, and let's suppose we have 4-bit of counter, so 3 down 0 and count. So we have declared all the ports and let's start the implementation. So suppose at every pauses of clock, so at always @ pauses of clock, let's begin. And so see, if here we are considering synchronous reset, so if reset is high, then our count value will moves to 0, or you can say count value goes to 0. So 4 down is 0, and otherwise let's consider here begin end, so it will be better. So begin end, and else if, so see, else if, so if enable signal is high, so your count value will increment by 1, and otherwise your count will remain as it is. So your count will remain as it is. So this is how you can implement your design code of 4-bit synchronous counter. So let's take an so let's take an end module here, and we have done with the RTL part. Let's start the verification part. So see, verification part is more important as compared to the RTL part. So module TV, and here we are not going to consider any hash delay. We are using task to do this, and this is the best practice you can also apply in your test bench creation. So we have considered module and end module. Now let's list out all the signals. So reg, wire, so let's list down all the signal: wire, clock, reset and enable, and then reg, count. And since count is of 4-bit, so 3 down 0 count. Okay, now let's consider this and connect to our DUT. So write it down like DUT. So this is how we have connect our design with our test bench. Now let's start implementing our test bench. So first of all, generate a clock. So let's generate a clock, initial, begin, end. So initialize your clock with initially 0, clock is equal to 1 tick B0, and then let's consider a forever loop. So forever #5 clock is equal to negative of clock. So this is how you can generate your clock in test bench. Now let's create a task. So first of all, we have to create a task for our reset. because whenever your reset value goes high, so your count value will moves to 0, and if it is low, so you can perform your operation, either your enable is high or low. Okay, so we have considered one task reset and end task. So see, first of all, let's consider our reset signal to high for some clock cycle. So we have considered reset signal to high for some clock cycle, let's say hashtag 10 time unit, and then we are keeping it slow for the rest. Okay, so here whenever your reset signal is 0, you can able to achieve your task. So this is how we have configured our reset task. Now let's consider another task, enable task. So we have considered task enable, and here we are giving enable as an input. So let's consider one instance name env and end task. So let's assign the value of enable. Okay, I hope you are getting this thing, and still if you have any doubt, then you can mention me in my WhatsApp group or Telegram group, which link are in description. Okay, so here we have considered enable signal, and now let's consider initial begin end. Now let's call the reset task. So we have called the reset task. So see, whenever we are calling our reset task, so it will start from 0 simulation time. So see what happened in 0 simulation time, at time 0 it will goes high, so it will keep remains high up to 10 time unit, and after that it will go slow. Like, so see, first of all we have to check our all count, like it is going up to 16 or not. So suppose we are considering repeat 17, and we are see, we are adding delay only by doing this. So we are waiting for 17 passes of clock, and after that we are again keeping our reset to low. So see, we are calling our reset, that means we make our reset low. Okay, so by doing this we make our reset low. Now let's configure the enable signal. So our task was enable. Now first of all let's pass the value 1. So see, whenever your enable signal value was 1, so it will keep on incrementing your count if reset is low. Okay, and then let's make the enable signal low here. So let's make it low, enable 0, and let's do this for some clock cycle. Let's take, or see, let's consider it for 2 clock cycle only. Okay, so we are considering our enable low for 2 clock cycle. So repeat 2, and we are repeat 2. So we are considering our enable low for 2 clock cycle. So let's consider 2 passage of clock. Okay, and then after that we are calling our reset, and then also we are sending our enable to 1. So this is how we can develop our test bench. Now let's include the dump file to see the waveforms, initial, begin, and end. So $dump file dump.vcd and $dump waves. Okay, so this is how you can implement. Now let's see the waveform, whether we are getting our expected output or not. So open epwave. Now let's run the code. Okay, so here it is showing error. Oh sorry, like here we have to declare it's a reg because it's an test bench part. So our input should be reg and the output should be wire. So this is how you can implement. Okay, now I hope it will be fine for now. Now it will be solved. Yeah, so see. Okay, so here you can see, like, let me maximize this. Okay, so here you can clearly able to see whenever our reset signal goes low, so it start incrementing from here. So it will go 1, 2, and up to it will moves to F, and then it will roll out to 0 and again 1. So here you can see our enable signal goes low. So what it means, it will keep remaining our count signal as it is. So it is keeping remaining the count as it is. So here also we are getting 1, and after that again here we have keep our enable high, so it will start incrementing. So this is how you can also implement. And still if you have any doubt, so you can write it down in comment section, and you can also discuss with me. Okay, so thank you.